Welcome to the video 2.4 on motion on an inclined plane. We have talked about free body diagrams previously, but in those cases the motion was not on an inclined plane, it was on a flat surface. So here we need to take a look at what happens to free body diagrams if our object is on an inclined plane instead. It adds a little bit of a complication to things. Let's assume that this object is at rest and that the inclined plane is at some angle theta. Okay, when we think about the forces on the box as it's sitting there, we have to keep in mind that because it is at rest, the sum of the forces should be 0. And so if we do a quick sketch of all of the forces on this box first, then we can put it into a free body diagram without the box and the inclined plane in it, but still represented. So first of all, we know that if it's at rest, then there has to be some frictional force heading up the plane, otherwise it would slide down. There also, because there's two surfaces in contact with each other, there is the normal force. Now note that the normal force is perpendicular to the surface. This has not changed from when we had the object on a flat surface, but it is more pronounced now. So it is more important to remember that now, that the normal force has to be perpendicular to the surface. The other force that's acting on this object is the weight, the force of gravity. Now notice that the force of gravity is no longer parallel to the normal force. Instead, it is going straight down. The direction of these two forces is very important for you to keep in mind, because without having them in the right direction, you're going to end up having issues with figuring out whether these are balanced or not. Now what we can do is we can take these forces and get rid of the box and the inclined plane behind them. But here's a little trick. When I do this, I'm going to slightly rotate the whole force diagram so that the normal force is pointing directly up and down, and the frictional force is pointing horizontally, which means that my gravitational force is no longer going to be pointing straight down. It's going to be at an angle. And if you think about it, I'm basically taking the plane of the incline and I am lowering it down. And when I do that, when I rotate this down, the force of friction is going to rotate outwards. So my force diagram then becomes, we have my box, right? Free body, so it's just a point. I have frictional force going to the right as it was before. I have my normal force going straight up. But now my force of gravity, or my weight, is going to be going at an angle. And the angle that the force of gravity makes is theta. It's exactly the same angle as the incline. Now we could go ahead and prove this with geometry, but we're not going to. If you have more questions about this, then make sure you ask me. But otherwise, you're going to be rotating your free body diagram, your force diagram, so that the friction and normal force are in horizontal and vertical directions. With this being the case, now we have to look at how do we know what forces are equal to each other, because this object is at rest. So if we look at gravity, gravity now is at an angle, so we have both a horizontal component to it, which we can call FGX, and a vertical component to it, which we can call FGY. Because again, this is at rest, that means that the sum of our forces have to be 0. If the sum of the forces are 0, then that means that this is true in the x direction and in the y direction. So the normal force should equal the force of gravity in the y direction, which, if we take a look here again, it's a right triangle. So that means that the force of gravity in the y direction is Fg cosine theta. And remember, Fg being the weight of the object is really mg cosine theta. Similarly, for the x direction, then that means that the force of friction should be equal to the force of gravity in the x direction. which similarly to the y is the same as the force of gravity times the sine of theta, which means that the force of friction should be equal to mg sine theta. This is important because we can then say, oh, those two should be equal, these two should be equal, if it's at rest. If it's not at rest, and there will then be an acceleration, and if there's an acceleration, then the size of these forces will be different. The reason why it's important to figure out if what's equal and what's not is because chances are you're not going to be given something here. Maybe you're going to be asked to find the normal force, or maybe you're going to be asked to find how much friction is required to keep this box from moving down the plane. Either way, you need to know what's going on so that you can determine that. You might even be asked, what would the acceleration be? Well, remember, if it's at rest, it would be 0. But let's think for a minute, what if it was sliding down the plane? If it is sliding down the plane, then the forces are no longer equal to each other. In the y direction, they will still be equal to each other because it's not taking off of the plane. It is not hovering in space. So the y forces must be the same. However, the x forces are no longer going to be equal. All we can say at this point, without giving any more information, is that if it's sliding down the plane, then Fgx must be greater than the force of friction. Now, if we had numbers, we could go ahead and solve this and find out what that would be, but it's important to understand that that's what would have to happen in order for it to slide down the plane. The force of gravity in the x direction would have to be greater than the force of friction. If we keep in mind what this really means, then, force of gravity in the x direction, we said, is mg sine theta. And remember, the force of friction is mu f sub n, or normal force. Normal force is mg cosine theta. So according to this, then that means that sine theta must be greater than mu cosine theta. This gives us a general idea. Again, if we knew more about the object and what the coefficient of friction was between the objects or anything else, we could figure out either the angle that it was at, or we could find out the force friction or anything like that. But the important thing to realize is that if there is motion, then the sum of the forces is no longer going to be 0. It might still be 0 in one direction, but definitely not in the other direction. Similarly, we could figure out what's going on if it was going up the ramp. If it's going up the ramp, then that means there's obviously another force involved, so we're not going to worry about that right now. But keep it in mind because you can still figure that out. Let's take a look at some problems dealing with forces on inclines and requiring us to make free body diagrams. The coefficient of kinetic friction for a 22 kilogram bobsled on a track is 0.10. What force is required to push it down a 6-degree incline and achieve a speed of 60 kilometers per hour at the end of 75 meters? Well, let's make a quick diagram first. We have our ramp. It is at 6 degrees. We have our bobsled. We know that the ramp is 75 meters long. The final speed is 60 kilometers per hour. We know that the mass is 22 kilograms. We know that the coefficient of kinetic friction, mu, is 0.10. And we know that we are looking for what is the push force that would allow this to happen. A lot of information, some of it doesn't necessarily seem to be all that related. So let's draw the force diagram. And again, I'm just going to do a quick sketch of it on the incline itself. We have the normal force. We have the force of gravity. we have the force of friction, and we know that there's a pull force. We just don't know how much. So if I turn that a bit, and again, I'm looking for that pull force. Well, if there is in fact a pull force and it is moving and it seems to be accelerating, then that means that the sum of the forces is going to equal to MA, not equal to 0. So in order to find that, we have to find the acceleration. So let's start by finding our acceleration, and then we can figure out the forces based on the sum of the forces part. To find the acceleration, we know that we don't have anything to do with time here, so we have to use that V final squared is V initial squared plus 2ax. There's our a right there. Well, we can rearrange this equation so that acceleration is v squared minus v naught squared over 2x. Keep in mind, however, that if we want this all to work out in nice units, and our distances in meters and our masses in kilograms and our speed cannot be in kilometers per hour, it needs to be in meters per second. So the first thing I need to do is I say that our final speed is 60 kilometers per hour. I need to change that to meters per second. So 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. That gives me a final speed of the bobsled of 16.6 repeating meters per second. So if that's my final speed, I can go ahead and use this equation for acceleration and say my acceleration then is 16.6 repeating squared minus 0 over 2 times 75, because the ramp is 75 meters long. That gives me an acceleration of 1.852 meters per second squared. So now that I have my meters per second squared, I can go ahead and use Newton's second law, the sum of the forces equals ma, and find out what the push force is. So in the y direction, again, the bobsled's not going to go jumping off of the track here, hopefully. So we're going to assume it doesn't anyways. And we're going to then say that there's no acceleration in the y direction, so it must just be in the x direction that we're looking for. In fact, if we make the assumption that there is no acceleration in the y direction, then again, the normal force here has to be equal to the force of gravity in the y direction. And so we know then that the normal force is going to be mg cosine theta. This happens often, so keep this in mind. With that, we can then look at the sum of the forces in the x direction will be mass times acceleration in the x direction. That will come from looking here. We have force of gravity in the x direction. We also have the push force in the same direction, it's in the direction of motion. And opposing that, we have the force of friction. I'm looking for FP, remember. I want to know what is that push force. So I'm going to rearrange this equation to solve for FP. So that means that FP is equal to MA in the x direction minus FGX. Remember, FGX is mg sine theta plus force of friction. Remember, force of friction is mu f sub n, so mu mg cosine theta. So now that we have this, we can simplify this a little bit more before we put any numbers in. We can pull an m out of all of it and get ax minus g sine theta plus mu g cosine theta. I guess I could have pulled the g out of each of these last two terms as well, but we'll just leave it like that. So then the force of the pull, whoever's pushing it rather, I guess, not pulling it, are they? No, they're pushing it, is 22 times 1.852 minus 9.8 sine of 6 plus 0.1 times 9.8 times cosine of 6. We plug and chug that in, and we find out that the bobsledders need to push the bobsled down the incline with a force of 39.6 newtons. So again, in order to solve this problem, the first thing we need to do is to draw our force body diagram. Second thing that we should do, or maybe this is the first thing we should do, we can interchange it, write down what we know and what we don't know. Then we find the equation, F equals ma, that we can use, some kinematics equations that will help us along the way, and then basically do a plug and chug and solve it through. Let's do one more. This one's a little bit more difficult in that we have two boxes. We have a block of mass m1 lying on a frictionless, ooh, I like these, frictionless inclined plane. It is connected to mass m2 by a massless cord, also very nice, passing over a pulley. Determine the formula for the acceleration. Notice it does not say find the acceleration, just find the formula for the acceleration for the system of two blocks. In order to do this, let's first do the thing that we always do, which is draw a free body diagram. Although I'm not going to draw the whole free body diagram, I am going to draw the forces on the masses. So for M2, we have the weight pulling down, M2G. We have the tension pulling up. And that's it. On the M1, we have tension pulling it up. We have a normal force. It is frictionless, so we don't have to worry about that. And we have the weight of the box. We can put it as Fg, force of gravity, but no, let's write it similar to how we wrote the other one. So this would be M1G, keeping in mind, of course, that it is at an angle theta compared to the normal force. So let's take a look at the first mass to begin with. The sum of the forces in the y direction are going to be 0, because again, it's not flying off the ramp or diving into the ramp. So because the sum of the forces are 0 here, that leads us to the same equation we had on the last page, which is the normal force is m1g cosine theta. The sum of the forces in the x direction, for box 1, is not equal to 0. It is equal to m1 times the acceleration in the x direction of 1. And so that, again, the x direction, we have tension force, and then we have the x component of weight. So it is m1 g sine theta minus the force of tension. Similarly, we can look at m2 and say there is nothing going on in the x direction, so we can ignore that completely. So the sum of the forces in the y direction are not going to be 0 either. They are also going to be equal to ma, and it's just the difference of the two forces acting on it. So Ft minus m2g. Well, notice that there's a force of tension in both of these, so I'm going to solve this one down here for the force of tension, and the force of tension is M2AY2 plus M2G. So we now have all of these equations that deal with forces, but I want a formula for the acceleration. So I know that I need to figure out how to combine these forces and solve for A. But there's like 5 different A's going on here too. Let's see. There's an AX1, there's an AY2, and then there's just acceleration that we're interested in. But because they are connected, the acceleration in the x direction of box 1 is the same as the acceleration in the y direction of box 2. So we can just call the two of them acceleration. And again, this is because they are connected here with the rope. So if that's the case, then I can take this first equation and say m1a is equal to m1g sine theta minus the force of tension. But I have an equation for the force of tension here. So I'm going to substitute this into there, and it's going to become minus m2a minus m2g. I am again, remember, looking for acceleration. So I'm going to move my accelerations all to the left. m1 plus m2a is equal to m1g sine theta minus m2g, which we can make a little bit nicer here, a little bit neater. We can pull out a g from both things on the left-hand side, divide the right-hand side, and this leads us to the formula for acceleration of this system being gravity times m1 sine theta minus m2 over m1 plus m2. So not the most pretty of formulas here, but you can see that we can take a fairly complicated system and we can break it down into the sum of the forces in the x direction, the sum of the forces in the y direction, using Newton's second law that F equals ma, and then understanding that they have some things in common. In particular, the force of tension is the same for both of them, and because they are connected with the cord, then the acceleration is the same for both blocks. So knowing those two things are equal, then we can combine all of this information and we can end up getting this equation here. So hopefully this gives you a better understanding of how to do motion on inclines with forces in particular and Newton's second law. So bye for now.